Okay, we shall be starting now. Let me share my screen. Okay, I hope my screen is visible. Yes. Okay, so welcome to week 11 of the Joy of Computing Using Python course. So this is the penultimate weekend. I think your exams are also, I think, this week or next week. So second last week. So in this week we will be solving some problems of recursion and some also basic problems where we try to minimize the number of operations, which we shall see. We'll try to reduce the complexity of the algorithms. You don't need to know what that is right now, but we'll try to do our codes as efficiently as possible so that they run in the least amount of time, the codes, so that the codes run the fastest. That's what we will solve. A couple of examples regarding that. Okay. So during this session, you can just write your queries in the chat. I think only one person is there for now. Others will join hopefully. So yeah, if you have some queries, you can write down in the chat, and also you can just unmute yourself and just ask your questions when I am finished. Okay, so let's start with the first question. Okay, so the first question is like a theoretical question. So in this week's videos, you were taught like time date manipulation and stuff. So what does time return? So you know that this returns something in seconds, but what exactly is this? So what does time give you? So let's see in action what it means, what it returns, and then we'll try to understand what it actually is. So let's import time, then we just do time, and we get this big ass number. So what does this mean? Any ideas? So you can see that it's changing when I run it. Sometimes the fractional part. So any idea what it means? Soumya? Okay, so what this number represents is actually something called the Unix time. So what Unix time is like, this is the count of seconds since I think 1st January of 1970, I think it was. So this counts the number of seconds that have passed since this time, like 12 a.m. So this is the what this number time represents. It's just the number of seconds from since the 1st January of it. So why is this used? So this is used obviously to count time, but also to keep a uniform count of time since since this date. And yeah, this is like the same across all of the systems. So if you type this in your PC and another PC at the same time, then you will get the same results. So you can understand that both of them are synced to the same time. Okay, so that was a theoretical small question. So let's go to question 2. Okay, so question 2 is so we'll be going back a bit and we'll be trying to solve a recursive problem. So we want to write a recursive function to check if a matrix is an identity matrix or not. So if you know, if I think you had matrices in high school. So matrices are like so identity matrices are just only the diagonal elements will be 1, whereas all the other elements will be 0. So this is identity matrix. So we have to write a recursive function to check if a given matrix is an identity matrix or not. And yeah, so let's do it. So let's just do it here. So okay, so I'll be using Python lists. You can also do it using NumPy arrays. It will be easier, I think, somewhat. So let's start. So let's keep it side by side. Okay. So let's take a matrix as input. Let's call it M. So let's keep it as an identity matrix for now. A 2 cross 2 matrix. Okay, and we have to define a function. Define is identity. We'll do something here, and we'll just, and it will like return true or false. So we can just print is identity M, right? So now what should we write inside this function? What should be the parameters? So obviously the matrix should be a parameter. Anything else should be the parameter? So yes, there are actually different ways of solving it. So one way is to so let me just show it here. So one way to check if a matrix is identity using a recursive function is, so suppose let's consider this 3 by 3 matrix. So what we have to do is we will consider, say, the last row and the last column. We'll check that using for loops, and if they are correct, then we'll say then okay, this column and this row is okay. We have 0 zeros and 1 1 at the end. And now check the rest of the matrix, like check the next 2 by 2 matrix. So that is one way of doing it. So let's do that quickly. That should not take too much time. So to do that, we'll just check if for I in range, okay, let's get the length size first. Rows nr equals to, say, number of rows, that is length m, and nc equals to number of columns, that is len m0. So this is standard. So first we want to check the last column, and we also want to check the last row. Last row and last column. So yeah, so for I in range, say nr, we want to check yes, nr or say nr minus 1. We want to check if all of these are zeros, right? So we want to check if m I and c not equals to 0, then we can return that it is not an identity matrix, right? And also we have to do this check for the rows also. So we can do it something like this, nr and I return false. Okay, and finally we also have to check that the last number m n r n c equals to 1, or say not equals to 1, then return false. And if everything else is okay, then we have to return then we know that this part is okay, so we have to check the smaller matrix. So you can just do return is identity m, and we will go up to nr minus 1 and nc minus 1. Okay, so let's see. So this looks like our code is ready. Let's run it and check. Oh, we have some errors apparently, sadly. Yeah, sorry, this should be nc minus 1, this should be nr minus 1, and this should be minus 1 minus 1. Okay. Oh, it's still, oh, sorry. Okay, hopefully this is alright. Not alright. Okay, let's see what's wrong with this code. Anyone has any ideas? Okay, so we have not given the base case. That's the problem. Base case should be if m say n. Okay, one thing we need to check is assert that nr equals to nc, not square matrix. So for a matrix to be identity matrix, you have to, it has to be a square matrix in the first place. So we need to check that if the number of rows is not equals to number of columns, then it is not a square matrix, and then thus it is not a identity matrix. Or we can just return false if nr not equals to nc, return false. But yeah, this was just a check. Now the base case is when nr equals to 1, or say less than equals to 1. If we have only one row or one column, then we can just check that let's just do equals to, then we can just check that individual element, then return m 0 0 equals to 1. Okay, so now we are checking if it is 1 or not. Like if there is only one element in the matrix, then it should be 1. That's our base case. So now let's try to run it. Oh, it still shows 1 false. Okay. Okay, let's try to debug this. Let's see, let's just return some numbers so that we can understand where the error is coming from. Let's call it 1 2 and 3, and let's return yeah, let's see what we get now. We're still getting false. Okay, let's return 1 2 3 4, let's say return 5. Okay, nr not equals to nc. That's strange. Okay, so we cannot just take a shortcut matrix like this. I think that's the problem. So we need to actually find a shorter matrix. So let's just do this. let's just do this in a better way. Let's just do it. So for row in M up to -1, so we are leaving out one row, and then for and we want for each column we want to reduce the last element. So this is our new smaller matrix. Now this should work. Okay, so we are getting a 5. So okay, hopefully this is correct now. False. Okay, let's run it. Okay, now we are getting a true, so hopefully correct answer. Let's try some other combinations. We are getting a false and something else. Okay, so this works. Let's try with a bigger matrix. This should be true, yes, and if we do something else then it should be false. Okay, so our code works. So any doubts about this question? How to recursively check if a matrix is identity matrix? So I don't see any questions in the chat. Okay, then let's move on to the next question. So next question is something very similar, continuation of the previous question. So now you want to write a recursive function to check if a matrix is an upper diagonal matrix or not. So an upper diagonal matrix is just a matrix whose all the elements below the diagonal are zeros, and that's all you need to check. You don't need to check if the other elements are 1 or 0 or anything. Just need to check that these parts are zeros. So to check that, also you have to try to minimize the number of operations. So to minimize the number of operations, what you can do is just do the same thing as before, but instead of checking both the columns and rows, you just need to check this specific column, right? So if you have a matrix and you need to check only the first columns of that, right? Or you can think of we are checking the last row. If you want to go back one by one, so you can think that we are checking the last row if all are zeros except the last one. So to change this, let's change this code itself and try to update it for checking a upper diagonal matrix. So let's call it, let's just copy paste it. Let's write it here. Is upper diagonal M diag M. Okay, so we have our matrix. So now to change it, okay, let's also copy paste the input. Okay, that's not. Let's take input something like, say 1 2 3 1 2 4 0 0 0, something like this. So this is a upper diagonal matrix. You can see that all of the bottom elements below the diagonal, all of them are zeros. That's what we need, and we need to just print is upper diagonal M. Okay, we should print out the answer. Let's change this to Okay, so what do we need to check here? So uh, the base case here will change, so let's go one by one. So again, for a matrix to be an upper diagonal matrix, the number of rows and columns should be equal, so this condition will not change. Now if there is only one element, then we don't have a diagonal, there is no nothing to check below, so it's always true. So we'll just change this to true. Okay, and else what do we need to check? We just need to check the last row, right? We just need to check if the last row, all of the elements are zeros except the last one. So this is, we were checking the columns here, so we remove this. So this is, we are checking the last row, right? So we are checking the n minus 1th row. If any of these are not zeros, then we return false, and else it is obviously we can't say, we need to check further. And this was, we are checking if the last element is a 1, we don't need to check that again. So yeah, that's our code. Then we create our smaller matrix as before, and we do this again, we call this and return it. Okay, so let's run it, and yeah, it shows true. And if we change it to something else, then you can see that it is now false, right? Let's and if we change these numbers in between, then nothing else will change. Even if they are zeros, it will still be true, but if this is not, then it should be false. Yes, so our code works. So any questions? Okay, then let's move on to the next question. Okay, yes, let's do this. Okay, so next question. So we are given a list of points in Euclidean space, and we want to find a point, find the one which is closest to another given point. So you have a fixed point, say P, and we have a list of points, and we want to find which of the points in the list is closest to the given point. Okay, so let's do it. First we'll do it in a longer way, like if you don't know the shortcut, if you don't know the function on how to do it, then we'll do it that way, and then we'll see the Python function for it in a scikit-learn library. So okay, so you want to find so we have, suppose a point P is, suppose let's just say 0 0 or say 1 1, and we have a list of points, say 0 0, these can be fractional also, 0.1 or minus 0.5 or minus 1, let's say 0.1, let's say 2 comma 0, let's say, yeah, let's just work with these 1.1, 0.9. Okay, so some very close by points. We want to find which of these points in the list is closest to P, right? So doing it is intuitively easy, not very difficult. So we just need to write a function that will calculate the distance. So let's write that. So define distance between, say, P1 and P2. So we have 2 points, and we want to calculate the distance between these 2 points. And yeah, you know the distance between 2 points is the square root of the sum of the squares. So let's find out the sum of their squares. So you have or we just return I think sqrt won't work, math.sqrt, or we can just do to the power. Okay, something square root. Okay, and that something will be sum of squares of the x and y coordinates. So p0, let's say p0, p10, sorry, p10 plus p20, and we take their squares. So I hope you know that 2 times asterisk means power in Python. Just single asterisk means multiplication, and 2 asterisk means power. And then yeah, p11, oh sorry, the formula should be yeah, I forgot what the formula is, but I think this is it. Yeah, okay, plus p2 1, right? I think this is the distance formula, if I'm not wrong. If I'm wrong, then someone write in the chat. Okay, so we are here we are considering the function only for, say, 2-dimensional points, so x and y only. If you have multi-dimensional points, then you can just run a for loop and do the same thing, not a big deal. So like do it for each dimension. Here we only have 2 dimensions, so we just did for 0 and 1. And then so what we need to do here is just iterate over all of these points and then see which one is the closest, right? So we can do for so let's just make a distances list. Distances equals to so a shortcut here is you can map a function to a list, right? Okay, let's just do it normal way first. Say let's say closest CL equals to list 0. So initially we are just assuming that list 0 is the closest, like the first point is the closest. Okay, and then what we can do is we can iterate over the list now, and we have, so for p in list, let's just call it closest. For p in list, we want to check, we can start from L1 also. We don't need to check the first point again, since we already have assumed that the first one is the closest. So what we need to check is distance, if distance between, say, closest and p1, sorry, and p, which is our given point, is greater than distance between, say, the small p and the capital P, the original point. Then we need to say that this small p, this is the closest p, right? And then we just print the closest at the end. Okay, straightforward question. Okay, so according to this is the closest, which is it right? Is it really? I don't think so. Okay, again something is wrong. Distance formula is correct. Let's just print the distance to see what is our distance. It's not printing. This is not working. Oh, sorry, it should be minus here. The distance formula, not sum of squares. It should be, yeah, I think this is it. The distance formula was wrong. No one wrote in the chat, sadly. Okay, so now our distance formula is correct, and so this is so yeah, the closest point should be this. Yes, right. Any doubts about this? Okay, the other way, the quicker way to do it is using the scikit-learn library. Let's see. So if you just Google, say, Euclidean distance pairwise, then you will get this page, scikit-learn matrix pairwise Euclidean distances, and this is the function that we can use to do the same thing, but in a much faster and much faster way. Okay, and then we just need to take the minimum among all of this. So this can be used to get the all of the distances to all of the points, and then we just take the minimum distance, and that should be it. Okay, then let's move on to the next question. Okay, another relatively simple question. So any doubts about the last question, or? Okay, let's move on to this question then. So suppose you are given the coordinates of centers of two circles, and you are also given the radii, like radiuses of the two circles. So you have to calculate if one circle intersects the other or not. Okay, simple question. So the logic behind this is that we want to calculate the distance between the centers, right? So, and if the distance is more than twice the radii, like more than the sum of the radiuses of the two circles, then it is outside, and if it is less than that, then it is intersecting, right? So here we can just change this here itself. Let's say we have two centers, say C1, circle 1, and circle 2 center is, say, suppose I don't know, let's say 2, 5 some maybe, and then let's say radius 1 equals to, say, 5, radius 2 is, suppose, say, 1. Okay, so are these intersecting? Let's find out. So what we need to do is we just need to find the distance between C1 and C2. So distance equals to let's call it dist equals to distance C1 and C2. Now that we have the distance, now we want to check if this distance is more than the sum of the radii, or is it less than the sum of the radii. And if it just touches, then also it is technically not intersecting. We can consider three cases. If C1 if distance is greater than or is less than R1 plus R2, if the distance is smaller, then that means that they are intersecting. So we can print that the circles are intersecting, right? And if this is greater, let's do elif or else if. So if the distance is greater, then the circles are not intersecting, and else if they are equal, then print I think it's called tangent. The circles are tangent, like they are just touching if the distance is equal. Okay, so yeah, so this is like a very large radius. So if it tries something like smaller circles, then it will show that the circles are not intersecting. And what is the distance? Let's check the distance. Yeah, something unholy. Okay, so yeah, simple question. So this is how you just use the distance function again to yeah, get the. Okay, any questions? Okay, then let's move on to another question. So yeah. So again, so this question is firstly it's seems simple. Then we'll move on to a slightly more difficult version of this. So yeah, so the program is I think something that you already have solved earlier in this course. So write a program which takes say an input n and calculates how many prime numbers are there till n, says up to say from 2 to n how many, because 1 is not a prime number. So from 2 to n how many prime numbers are there. So if say n is 10, say if n is 10, then we have prime numbers, what are the prime numbers, 2, 3, 5, 7, yeah, that's it, no more. So we have 4 prime numbers till 10, so the answer will be 4. Answer equals to 4 since we have 4 prime numbers till n, right? So how do we do this? Again, this is relatively simple. So what we can do is define is prime function. Is prime, it will check a number n, right? So correct number n, why not, let's call this number. Okay, so what we can do is we need to check if what are the divisors of n, right? If n is divided by any number other than 1 or itself, then it's not a prime, and if it is not divided by any number other than 1 or itself, then it is a prime number, right? So we can just check for all numbers. If for say I in range, we start from 2 and then we go up till say n, so like this will go up to n minus 1 because range returns one item before. And then if we can just check if n is divisible by I, so percentage means modulus operator, which means the remainder. So if we divide n by I, what is the remainder? If the remainder is 0, it means that n can be divided by I, so it is not a prime number, right? So we return false. And if it cannot be divided, then we can't say just yet, we need to continue doing this till the end. Then we can just do return false, return true. So if it has no numbers between 2 and say n minus 1 which divides it, then we can just say it is a prime number, right? And now what we can do is we can just say run let's call it capital N. So what we can do is for say n in range capital N, so what we can do is we can check all of the numbers if they are prime or not, and if they are prime, then what we can do is like we'll increase a counter. So let's set a counter to 0, and we say let's start from say 2, we'll go up to n, so we'll do n plus 1. And yeah, what we need to check is if they are prime or not, and if they are prime, then we'll just increase the count. So if is prime n, then count plus equals to 1. Okay, then print count. So this is our code. Let's see if it works. So yeah, the answer is correct, it is 4. If you want to print, you can also print n. You can also see what are the prime numbers. So you can see 2, 3, 4, 5. Yeah, like the last 4 is just the count. So before that we have 2, 3, 5, 7. These are the prime numbers. So if we try say 100, now you can again see all of the prime numbers, and we have finally 25. We have 25 prime numbers in total, right? So let's, and say if you have say 1000, then we have 168 prime numbers. If you have 10,000, we have 1200, and you can already see that there is a slight pause now. Now what if you want to check till say 100,000? So now you can see it is taking some time to run, okay, because our code is not very efficient. Okay. So you can see it is now stuck because it's still running. It's taking some time to get the results because it's a large number. So that brings us to our next question. So continuations. So I think someone joined in between. So yeah, the question is, so we have to write a program which takes an input number n, so which is like capital N in our program. So input n, and calculates how many prime numbers are there till n, right? So for example, for 10, if n was 10, so if n is 10, then we have say 2, 3, 5, 7, 4 prime numbers. So the answer is 4. Yeah, and this answer came right now. So you can see that earlier, if you have small n values, then the answer is coming relatively quickly. But if you have large numbers, then it is taking quite a lot of time to run, right? So the question is, what if n is very large? Can we do it faster? The answer is yes, obviously. And using something called the sieve of Eratosthenes. So he was a mathematician, and he invented a technique for quickly finding out all of the prime numbers, right? And yeah, since you already have done time, let's also check how much time is required to run this code. Let's time it. So let's say t0 equals to time.time, and at the end say t1 equals to time.time, and then print time taken is say t1 minus t0. Let's convert it to integer and seconds, right? So if our n is small, say if our n is say only up to say 1000, and sorry, import time. Let's print it, round it up. Let's round up this to say 2 decimal places. Okay. So if you have calculating till 1000 n's, then we can see it is taking say 0.01 seconds. So what about 10,000 numbers? If you have to check 10,000 numbers, it is still taking relatively quickly, but you can see it was noticeable. There was a noticeable difference. And if we have say 100,000 or 1 lakh numbers, then it is taking a few seconds. Okay. So how can we make it better? Okay. So we can make it slightly better by one fact is that if a number has a factor, say if the number n has a factor of I, then obviously let's say the number n has a factor which is say a times b, right? And say a is smaller than b, right? So what so one thing that is a property is if a is smaller than b, then obviously b has to be greater than n by 2. If a is less than b, then b should be greater than n by 2. You can think of it. So you can think about it. It's a corollary or hypothesis. But yeah, so if you have one number which is less than n by 2, then the other factor of the number should definitely be greater than n by 2. So what we can do is we can just instead of checking till n, we can just check till n by 2, because if there is a factor, then that will be there before n by 2 itself. So if we do this, we can already see that n say by 2, you can already see that there it will take some less amount of time. So initially it took 44 seconds. So now let's see how much time it takes. Let's wait for a minute. Should take less than 44 seconds. And so this is like kind of, so you can see that it took like exactly half the time that it took, because we are checking half the numbers, right? So we can do even better, especially for larger numbers. There is another corollary that if there is a factor, it will definitely be within root n. So you only need to check actually till root n if a number is prime or not. So what you can do is you can just calculate this integer n by 2, and you can see so if we run this, not into 2, so it will be 0.5. So root 2, we are doing the square root, right? So we only have to check till the square root, and now you can see that it is much faster, right? So what can we do better? So earlier it was taking 44 seconds, then it took 22 seconds, and now it's taking just 0.3 seconds for 100,000. Now we can go up to a million. Now it will take some time, because still it will take a lot of time, but still hopefully should be done in relatively quickly, 6 seconds. What if we go even bigger? Then we run into some problems. So let's try to do it using another method, which is called this sieve of Eratosthenes method. So before that, any questions on this? Actually we should check till this +1. That's why the numbers were a bit shady. Now it's correct. So you should, because range is taking one less number, so you should do +1. Okay. Any questions? Any doubts? How do I download the hall ticket? So you're asking you are asking this in the wrong place. So you should ask this in the discussion forum. This is just a tutorial session, so ask it in the courses discussion forum. Any questions about the problem? Okay, hopefully not. So okay, for 1 million our new method was taking 6 seconds, I think. So can we do better? So let's do it quickly. So sieve of Eratosthenes, what this is what we will do is we will just so this is a method that will take even less time, but there's a catch that we need enough memory, because we need to store some more numbers. So there's always, when you are writing algorithms, in advanced algorithms, then there's always a balance between how much memory your code takes, like how much array space you require, and how much time you require. So if your algorithm requires more time, then it will require less extra memory. If your program requires less time, if your program requires more, vice versa, the time and the space. So that is something that you will learn later on. But for now, so what I'll just explain the sieve of Eratosthenes in a quick fashion. So what we'll do in this method is we'll just write down all the numbers first, one by one, up to n, 11, 12, say up to 15. Okay. So what we'll do is now we'll just first write down all of the numbers. Okay. If you are doing it by hand, then you will write down all the numbers, and then you know that 2 is always a prime number, and all the multiples of 2 will not be a prime number, right? So what we'll do is we'll delete all the multiples of 2 from this list. So we'll delete 4. We'll just write a dash here. You'll see why. So we are just deleting all the multiples of 2 from this list. I forgot to write 13. but okay. So now we have this, right? So now we have checked 2. Now we know that the next number 3 is also a prime number, but all the multiples of 3 are not prime numbers, right? So we'll remove all the multiples of 3. So we'll remove 6, which is already been removed, so nothing to do. 9, we'll remove that. So 12 is already been removed, and then 15 we'll remove, right? So next number is 4, but it has been removed, so we know that it is not a prime number. So we'll go over to 5, and we know that now 5 is a prime number since it has not been removed yet. It is not a multiple of any smaller number, so we'll remove all of the multiples of 5. But yeah, here like 10 and 15 have been removed. If there were more numbers up to 20, then we would have removed 20 now. Okay, so and this is how it goes. So now we can already see that we are already left with only the prime numbers, right? So see, this is the sieve of Eratosthenes, and so here we will require some extra memory to hold this array. So we need to keep track of all the numbers here. But this is much more efficient because you are just for each number you are just taking the rest of the array, right? And so if you check the complexity, I think it's about n log n, or say log n root n, something like that. It's very fast, you will see. So our this method for 1 million, our initial method, initial method took a long time. So our improved method, that took 6.52 seconds for 1 million points. So now let's see what this method takes, this sieve of Eratosthenes method. So for this, what we need to do is we need to first define say n is say 1 million. Is it 1 million? 1 2 3 1 2 3, yeah, 1 million. Okay, so what we need to do is first we need to create an array of this size, which we can call just is prime. Okay, and initially we'll just set all of the numbers to true. So true into say n, okay, or say n plus 1, because the first number will be 0, right? So this means so initially we are saying that all of the numbers are prime. Okay, but yeah, we can remove 0 is prime, not really required, but we can say is prime 0 and equals to is prime 1 equals to 0 equals to false, because 0 and 1 is not a prime number, so we can just remove it, but it's not required, right? So initially what we have done here is like we have written down all the numbers and written down that yes, they are all of the prime numbers, right, like we wrote down in the beginning. Now what we need to do is we need to find the first prime number. So let's do it with while, or we can do it with for also. Let's do it with for loop or while, why not, sorry, while so let's start with I equals to 0, the current number, or let's call it n, like before we were calling it small n. So while small n is less than equals to capital N, we'll do this. Okay, so what do we want to do? We want to okay, so n is not 0, we'll start from 2. Okay, so this is similar to what we did before. So here what we did before, here also we are doing the same, just using a while loop. So we are starting with 2 and we are going up to n. But what we need to do in this case is not to just check individual numbers, but we will just remove all the multiples of say small n, right? So you want to iterate over all of the multiples of so for say I in range. So you want to start from n, we want to go up till n plus 1, and we want to skip to only multiples of n, right? So this is the step, this is our range function, right? Actually, yeah, we need to start from say 2 into n, not n, because n is a prime number, so we need to start from 2 times n, and we'll go on in multiples of n, right? So we'll remove 2n, 3n, 4n, all of these we'll remove, and by removing, what we'll just do is we'll just set is prime of that number n, not n, sorry, I equals to false, right? Okay, so what we are doing here is basically we are selecting a number n, right, and then we are removing all of the multiples of that number from the is prime. And yeah, obviously if n is already not prime, then we have already removed its multiples. So something is wrong. Okay, no, correct now. Okay, so if a number is, if n is prime, n, and if n is not prime in the first place, that means, suppose for example when we reached 4, we know that 4 is not a prime number, so 4's multiples have already been removed already, so we don't need to do it again. So if not prime, if n is not prime, then we don't need to do anything, we just can continue or do yeah, n plus equals to 1. Here also we need to n plus equals to 1. Yeah, okay. Or it's something like if n is prime, then you do this check, right? Okay, that's better. And now what we need to do is we need to just count the number of trues that remain in the array. So we can just do that with sum of say is prime, and we'll just print it, print sum of is prime, and hopefully it should give us the same answer as before. Yeah, you can see that gave us the same answer, but you already saw that it was a lot faster. Let's check the time, import time, and say let's start from right here, t0 equals to time dot time, and let's copy paste. Okay, so let's see, for a million it's taking less than a second, okay, by this method. So if we are using our old method, it was taking around 6.52 seconds. You can see this is the old method. It took 6 point something seconds, and using this sieve of Eratosthenes, we are getting it in like less than a second. So this is very even faster than our improved method before. And if it like keeps on growing, so if you just do it 10 million, you can see that it will still take only a few seconds to run. Okay, so any questions about the sieve of Eratosthenes? If you are not sure of the spelling, you can just Google it, sieve of Eratosthenes. Like this was a mathematical thing, not really a computer thing. So yeah, you can see for 10 million it is taking like the same time as the normal method is taking for 1 million. Yeah, so any question about this method? Else we can wrap up. I'll wait for 5 more minutes if anyone of you has any questions. Let me stop the recording.